Hello everyone and welcome to the Shell Ideas 360 webinar. Today from Shell we have Albert, Janssen and Frank Niele who are going to talk to us about the Energy Water Nexus. We will have a Q&A session at the end, so you can just type all your questions into the chat box of this meeting software. Questions should only be on the subject of this webinar, and any other questions can be directed to shellideas360@shell.com. We will cover as many questions as we can on the call, but if we run out of time, the remaining questions will be answered offline and shared later along with the recording of this webinar. So now I'll pass you over to Frank and Albert, who will introduce themselves before going into the presentation. Thank you.
Yeah, thank you very much, Karen. It's Albert Janssen speaking. First of all, I would like to say that I'm very honored to take part in this webinar. I'm the manager of the Global R&D Water Program at Shell, and I do have a background in engineering and in research. Let me check at this point in time. Can you see my screen? Karen?
Yeah, we can see your screen. But
my screen here.
Oh, okay. No, we can see your screen, but you might want to click that hide control panel because we're seeing a black box at the moment over your presentation. So the little orange arrow.
So what it's, I see something completely differently here.
Really?
Yeah.
Hide control panel. Oh, you did it just before.
What it says is, now what it says, it's pausing screen sharing. So
pausing screen sharing. Oh, okay. No, you don't want to.
Since you put me on mute, you know, my screen is flickering, so I cannot control it anymore.
Okay, I'll take the presentation off you.
Yeah, if you want.
I'm just going to quickly take it off you, and then I'm going to give it back to you, just to reset it, just to make sure it's going to work. Okay, so if you show your screen now, Albert, yeah, that's fine. That's looking very good on my side.
Yeah.
Better for you? Okay, great. Thank you very much.
Yeah, thank you, and apologies for the interruption. So I left at the point that I was explaining that I am coordinating the water program in Shell, and I think it's also important that you realize that you can imagine that I can only show you a high-level overview together with Frank today. To the next slide here. So this is a disclaimer statement. It's a mandatory slide that we get from our friends in the legal department. It actually means that certain definitions that we use, like reservoirs, etc., they belong to a specific definition, which I may not always use in this presentation. So in this presentation, I will actually like to start by mentioning that Shell has been studying the energy, water, food connection, or stressed nexus, for some time. And what we would like to describe today is how we see this connection and also explain what energy companies like Shell can do about it. I also plan to highlight some areas where more work is needed and where we are driving new solutions. But before I do this, let me first frame this story of global energy.
Hi, Albert, can you hear us? You've cut out a little bit actually, and we can't hear you anymore. Albert, are you still there? Sorry everyone, just bear with us. It seems like the connection this morning is not the best because Albert is cutting out all the time. We'll just give him another minute to see if he can come back.
I will send him a message through MOS.
Thank you, Frank.
Huge. Growing at a promising rate, which is quite by as much as 1/4 of the world's energy. And at the same time, this means that oil and gas are going to remain critical in the global energy mix for decades. So clearly and urgently, there needs to be a step change in how we find and produce energy sources, and we all have to become smarter about using energy more efficiently. I have to find my pointer here. Karen, can you give the presentation back? In some way, Karen, I lost my pointer. Karen, can you hear me?
Sorry, I was on mute. What I'll do, I'll just take it off you and give it back to you again. Just might need to restart it.
Yeah, it seems that my computer went on idle.
Right. Yeah, no, you did cut out for a minute there actually. So can you show your screen again and see if you've got your pointer back?
Well, actually, my computer is not responding at all.
No? Oh gosh.
No.
Okay, sorry everyone on the call. If you just bear with us, can you quickly send me your presentation, Albert, and I'll show the screen?
Yeah.
Or is your computer completely frozen? Otherwise, I should have a copy as well, if you haven't.
It is frozen.
It's frozen.
Yeah, it is frozen. It's not responding at all.
Okay. Give me a second. I should have a copy of your presentation. And then we can just carry it on. I'm not sure if you can see my screen though.
So it's now unfrozen again.
Oh, it's unfrozen? Should I give you back controls?
Yeah.
Okay, Albert, I'll give you control again so you can show your screen and see if that works. Okay, we can see your screen again now.
Yeah.
Okay.
So let me move on. So the difficulty is I have to find my pointer here, and it's all kinds of gray. So here it goes. Yes.
Great.
Well, apologies for that. So you have to understand that energy supply is not the only area that is under pressure. Water is another key area. And if current water consumption trends continue, the world is expected to need 30% more fresh water by 2030. Our growing global population is also putting pressure on water supplies, both directly and indirectly, through increased demand for energy and food. World demand for food is expected to rise 50% by the same time. So you can already see how these things are interconnected. On the one hand, to deliver more water and food, you need more energy. And a lot of energy is consumed in processing, transporting, desalinating, and recycling water for consumption. And also modern agricultural methods are very energy and water intensive. But luckily, there's a growing awareness that the path to a more sustainable energy future will require society to consider water, energy, and food systems. All three are under increasing stress, and we need integrated solutions to tackle the challenge. And that's why Shell launched a new phase of strategic thinking. Our company has to be better in understanding how the water, energy, and food stress nexus is connected. So most energy cannot be produced without access to reliable water supplies. Water is, for instance, used for hydrocarbon extraction and refining, but also to unlock tight gas using hydraulic fracturing. On the other hand, water is also produced in the process of producing oil and gas. And this is what we call produced water. And you have to realize that we produce 10 times more water than oil. To meet future energy and water challenges, we need innovative and integrated solutions to tackle both energy, water, and food stresses. And a part of this, in Shell, we created the Water Center of Excellence. And this vehicle coordinates in a comprehensive way methods that we develop to challenge this water stress nexus. And one of the key research areas that's being investigated in this Water Center of Excellence is a program that's being executed by Frank Niele. And I think this is a nice time to move on to his presentation. Frank, the floor is yours.
Thank you, Albert. Well, yes. Hi, everybody. My name is Frank Niele. I work in the water technology platform that Albert just introduced. Part of that platform is the so-called policy support program unit, and in that unit we are trying to understand, say, business risks related to water, and if there is business risks identified, we are trying to find solutions to mitigate the risks. Well, one of the things that you need to start with is if you want to assess quantitatively water-related business risks in the energy world, one of the things you need to start with is getting a picture of the numbers, so accounting. And the next slide is the first slide that shows important, I think, numbers to get a view of what the water energy nexus is. We focus on water energy now. If you look at water for energy, then the amount of water in volume terms needed to produce energy today is about equal to the water use which is going to domestic applications globally. As many people often say that most water is used for agriculture, which is true, by the way, but it doesn't mean that there is no issues with other say sectors in the economy. Water use for energy is really significant, and you understand the significance by realizing that it's about equal to domestic use. The other way around, energy for water is also significant, about 8%, and this is a recent United Nations say number from a United Nations report. About 8% of global energy generation is used for pumping, treating, and transporting water to various users. So it's really, the water energy nexus is really huge. If we go to the next slide, we see an almost identical picture, but not completely identical. The only thing that's added here is the word fresh for water. And I think it's very important to realize that when people talk about water scarcity, they mean fresh water scarcity. So often cases, water stands for fresh water. There is where the issues are today already at some places in the world and will become much more serious in the coming, say, decades. That's what the next slide shows. The next slide shows what's called the water energy gap between water supply and water demand, and this is fresh water where we talk about it. Today you see already a gap of about 5% it is between reliable freshwater supply, that's the bottom line, and the demand, freshwater demand. It sounds a bit strange, a freshwater gap, because supply can never be higher than demand, you should say, but this gap is filled by taking water from freshwater aquifers, and that water is not completely replenishable or renewable. So the freshwater gap today is, for example, in quite some places in the world, in Mexico, for example, irrigation water is taken is done by taking water from fossil freshwater aquifers, which really is an issue that we have, because it means that in a few decades irrigation suddenly becomes difficult if the freshwater aquifers go extinct. But this gap between say reliable, renewable freshwater supply and demand is growing in the coming decades quite rapidly, up to 40%, which is a real issue. If we go to the next slide, we see that there is indeed a freshwater issue, but it's important to realize that fresh water is only a small part of total water. At the left part of this picture shows that 2.5% of total water is fresh, the rest is saline, and from this 2.5%, that's again remarkable, I think, only 0.3% is what we see as fresh water, namely surface water, water that flows through rivers and is in lakes, etc. So 70% of the freshwater part of the pie is solid in ice caps and glaciers, 30% is in groundwater layers, and only 0.3 in river basin runoffs. And that's what the next slide shows. It is this river basin runoffs that we tend to talk about. So only 0.3% of the 2.5% total water is flowing through these river basins, which start at usually in mountains with the melt of glaciers. It's underway, filled by rain, and ends up in the oceans. It's this river basin runoffs that we usually people talk about when they talk about say water scarcity, water stress, water security, and also water footprint. The next slide is a slide about the water footprint that can you go to the next slide, Albert, please? Okay, this is perhaps slides or numbers that you all have seen. I'm living in the Netherlands. We regularly see in newspapers references to this water footprint. We see it on television. You see it in the industrial journals. Often we see these huge numbers associated with the production of, for example, milk, bread, meat. It's the water footprint network. People say that it costs 1,000 liters of water to make 1 liter of milk, 1,600 liters of water to make a kilogram of wheat bread, etc. But this is about fresh water, and it's important. We see the colors already in the left side of those pie diagrams. It's important to realize that the water footprint calculation includes not only water taken from river basins, but also, and that's what the next slide shows, water from, say, the green water footprint and the gray water footprint components. And before we go into blue, green, and gray, it's important to understand what the water footprint means, how it's defined by the scientists. The water footprint indicates so-called water consumption. And water consumption is not what we do at home, if we tap water from the tap, but water consumption is defined from the river basin perspective. Perhaps you remember the picture 2 slides ago. Consumption is defined as water that is withdrawn from a river basin runoff and not returned to that river basin runoff for reuse downstream the basin. That is how consumption is defined. If you define it this way, from the river basin perspective, then the water footprint network, that's a network of scientific institutions, discriminates between blue, green and gray water, with blue water seen as surface and groundwater. So if you take from the surface or the shallow groundwater layers, you consume blue water. But green water is defined as soil water, which in fact is rainwater, which explains that all those biomass-based products quickly have huge footprints. The grey water footprint is a bit different one. That's not measurable, but it's calculated. It's a virtual volume which is needed to clean a contaminated discharge by dilution, and it's the volume that you need to dilute, which is called the grey water volume. And so that's about discharge. That's about often effluents from agricultural and industrial and domestic usage. If that usage leads to contamination, you don't treat it, then the thinking here is look at the volume that you need to add to the effluent to reduce the concentration of the contaminants in such a way that is acceptable, say, from an environmental and a regulatory position. So that's grey water. If we go to the next slide is to show that if we, again, very huge numbers for a kilogram of beef, 15,000 liters, a kilogram of cotton, 10,000 liters. We say in Shell that if we do water accounting, and we hardly use biomass only for biofuels, but we think that it's a bit confusing to look at rainwater intake, because then you cannot, we think that if we account, that you do need to account in such a way that you can make like-for-like comparisons between oil-based, gas-based, coal-based, biomass-based. Doesn't matter what sort of energy pathway you look at, you need to do a form of accounting that makes everything comparable on a like-for-like basis. So we do not look at the green component. We also don't take the grey water component into account, because we say in Shell that if we discharge into whatever it is, a river basin or a lake or an aquifer, then we treat the water in such a way that it's in compliance with the regulations. So we don't need that grey water footprint. So we focus on the blue water component. We focus on that what's taken, fresh water, what's taken from a river basin runoff. And we do that from the industrial perspective, because we do industries, we do operations. So if we go to the next slide, we have a simple picture from that shows our accounting perspective. We sit in an industrial operation. We look at what we take from a river basin runoff. That's what we call withdrawal. We look at what we discharge into a river basin, and the difference is consumption. And that consumption can go, for example, through evaporation, which is a clear example of water consumption. That's that water that evaporates, not returned into a river basin and lost for next consumption downstream the river basin. If we go to the next slide, and we want to understand the water energy nexus, we need to look at the water intensities, the withdrawal and the consumption intensities that are associated with an energy pathway. And an energy pathway usually goes from energy sourcing to the making of an energy carrier which is usually or mostly a fuel, can also be electricity, to energy usage. So a pathway goes from energy sourcing to an energy carrier production to an energy service, which is the use of that fuel. Well, if you want to understand the water intensities associated with an energy pathway from source to surface, then you need to look at sourcing and manufacturing. So the second step, you do not need to look at the end step, because the usage of an energy carrier doesn't need water. You can burn gasoline in a car and you don't need water for that. But you do need water for the sourcing of oil or gas, and you do need water for the production of gasoline at the refinery. So we look at energy sourcing and fuel production, both withdrawal and consumption. And we've done that for a whole range of energy pathways, from oil and gas based to also biomass based to also solar and wind based, etc. And the next slide shows a bit complex picture of the results of this study. So this is one of the first, well, I think the first, say, study which shows a rather complete picture of water intensities, so consumption and withdrawal intensities of a whole range of energy pathways from source to surface. And if you look at this picture, it's important to understand the axis. Well, the x-axis is clear. That's depicting, say, the energy pathways that we talk about. The y-axis is the freshwater intensity expressed in liters of water needed to produce a gigajoule of LHV, and the abbreviation LHV stands for lower heating value, and say the heating value is a measure for the quality of a fuel. You produce a fuel to combust it, to get energy from the combustion, and that's why we use the lower heating value as a unit of management for fuels that makes, say, different fuels comparable on a like-for-like basis. So we looked at the consumption and the withdrawal intensities. Consumption is the red bars in the graph, and the blue represent, say, withdrawal. So we've looked at withdrawal and consumption intensities, and you see, and that's important to realize, that the y-axis is a logarithmic scale. So the right parts of the graph, you see sugarcane, maize ethanol, soybean, but also another one. I will not discuss all of them because we do not have time with that. We do have a paper, by the way, that if you're interested, you can ask for the paper, and then we will send it to you. But what you see is that biofuels can have very large water intensities. We needed, in fact, the logarithmic scale to get biofuels on the graph. But the biofuels one also have, say, two type of bars, more saturated colored ones, the dark red and the dark blue, and less saturated, lighter blue and light red. And that is to discriminate between biofuels produced from biomass in rain-fed areas and biofuels produced from biomass in non-rain-fed, thus irrigated areas. And the message is that if you produce, if you need to produce biofuels from biomass from irrigated fields, then your water intensities really explode. They become very, very large. That costs lots of water. But if you produce biofuels from biomass from rain-fed areas, where you do not need to irrigate, then your water intensities are way, way, way smaller. And if I go to my first, say, observation, one of the first, say, conclusions that you can draw from this study, that's the left top box of this slide, that says that both, say, first generation rain-fed biofuels and second generation biofuels are in the same ballpark if you talk about, say, water intensities as oil-based biofuels. And perhaps to explain the difference between first generation and second generation biofuels is the following. First generation biofuels are biofuels made from energy crops, as we call them. So those crops are grown to produce biofuel, dedicated for biofuel production, while second generation biofuels are really different. That's biofuels made from waste, from food or wood production. Especially if you look at food production, if you grow a crop for consumption, then about 10% of the energy in the crop goes to that what we eat, and about 90% leaves in the waste. And we in Shell do lots of research, and others too, to convert that waste into fuels. And if you do that, the water intensity is, say, decided sort of, well, let's phrase it differently. If you use waste for the production of a fuel, then the water allocation goes to the primary product, which is the food. But that's why in this sort of analysis, and it doesn't in this analysis the water intensities for biofuels from second gen are also relatively low. That's the same ballpark as oil. The second conclusion, that's the middle box at the top line, says that oil-based energy pathways can have even a zero water footprint. And that's if you use saline water only. And quite some scientific papers, for example, from the Water Footprint Network, if you go to that website, sort of claim that oil-based energy pathways have a very significant water footprint. Well, that's not true. Can be a bit significant, but it's on average small, and it can be zero. If you produce water offshore, if you produce oil offshore, which is what happens a lot, then you don't take fresh water in. And if you have your refinery at the coast, which also happens a lot, then you can cool, for example, with seawater and don't use fresh water. So this is to show that you have a range, and there's huge differences, and lots of oil-based energy pathways have really a zero water footprint. The third observation from this, again we can make more, but this is what I like to show, is that gas, if you produce gas, either conventional or shale gas, that's the left part of the graph, the water intensities are really low. Also for shale gas. Shale gas is quite in the news, and it's said to use lots of energy, but if you look at the shale gas intensities, say per gigajoule lower heating value produced, the intensities are relatively low. We use water, but only in the first days or weeks of the shale gas production well, but when it starts to produce, you don't use water anymore. And there is, of course, other issues with shale gas, as we also know from the news, but that's not related to intensities. The water footprint only looks at intensities of, say, consumption, and we have added withdrawal here. So, well, that's I think enough for now about this slide. I'd like to go to the next slide then, which is the last for my presentation. This slide shows what sort of solutions we can try to develop if there is water stress. And if, again, water stress means freshwater stress. We say water stress, but we mean freshwater stress. And if you are in a freshwater stressed area, you have one of the first things you can try to do is reduce freshwater withdrawal from river basins, which is can be very important if you are, for example, an electricity company and produce power. Power generation uses lots of water for cooling. So it withdraws water and mostly returns 98% or something of that water because it's only used for cooling. But you need it. If the rivers say dry up or the water becomes too warm, then you can't cool efficiently anymore, and you need to do something. And reduction, so going to another sort of technology that uses less water for cooling is a good solution, say, direction. So the second thing is reduce not withdrawal but consumption, which means that if you take something from a river basin, return it as much as possible. Third one is, if possible, don't withdraw and don't consume, but try to recycle on site, which means, in fact, improve the water efficiency of your industrial operation. The fourth option is, we looked at freshwater now. We can try to improve freshwater, say, cycles, but you can also try to use non-fresh water. That is either rejected water from other operations, and we do that in Shell. We have made a first, say, beginning with that. We, at several places in the world, from the Netherlands to Canada, we use at some places municipal wastewater instead of fresh water from the surface. And another way is to not use fresh water but saline water if possible. You can do that by going to the coast with your operations, or take saline water from aquifers if they are there, which is also something that we do. And so this is a part of the solution space that is technology related. That's related to the operations that we do ourselves. But I think we all know that water is something that's very much say a system which connects all sorts of demands and supply, etc. And so the solutions, we should not only look at solutions by looking only at our own operations, but we should look at infrastructures. That's the last bullet. Try to improve the water efficiency of water infrastructure at large. And the last, say, addition says, if you look at the infrastructures, look also at green infrastructures. And green infrastructures are sort of water systems where we combine natural water functions with technologies that can really improve the overall water efficiency of the system and make it more resilient. Which means more stable with respect to all sorts of changes that come from changes in the environment. Okay, so that I think, Albert, is my contribution. So over to you.
Okay, thank you very much, Frank. Yes, let me try to find my pointer again. There it is. Okay. So building on what Frank just mentioned, namely that we need to rely on technology to manage our water footprint, I would like to show some examples here to you. And my first example is about one of the biggest projects Shell ever did, which is the Pearl GTL plant in Qatar. And this is a world-scale plant where we convert natural gas into 140,000 barrels per day of GTL products and condensates. So it's a huge plant where we upgrade natural gas into kind of diesel type of projects. And you may recognize it as V-Power when you go to the gas station. So let me briefly describe to you how this GTL process works, so you can also understand how it impacts on the water cycle at the plant. So if you look at the reaction equation at the upper part here of the slide, you can see that in the first process step of the GTL process, we oxidize methane, actually with a too small amount of oxygen, into hydrogen gas and carbon monoxide. You can imagine if you have an overdosing of oxygen, we burn it all into CO2, but since we have a substoichiometric amount of oxygen, we convert this syngas here, and this carbon monoxide is then subsequently passed over a catalyst where we make this hydrocarbon chain, and here the water. So what you can see is that the oxygen that we add in the first step of the process is actually knocked out from process as water. And the funny thing is that we produce as much water as hydrocarbons in this plant. So we're talking about huge amounts. Well, just to give you some background here, this process has been first developed in Amsterdam in the laboratories. And you can see here these very nice products. Well, you can already see it's very clean. It's like a water type of product, so very much unlike the regular gasoline or diesel that you buy. So it's characterized by the fact that it has no aromatics and also has no sulfur. After doing this laboratory testing, a pilot plant was started up, again here in Amsterdam. So this is really holy ground. And after the pilot plant, we started our first commercial operation in Tunu, Malaysia. That was early 90s. And then in 2011, this Pearl plant was taken into operation. So what it does with respect to water is that it treats and recycles all the processed water, as just very nicely described by Frank. And in that way it enables its own water supply. So it's really self-sufficient, and therefore it actually doesn't draw upon the scarce water resources in Qatar. And it's also a huge water stream. And we're talking about 45,000 cubes a day. That's a lot of water. If you compare it, for instance, to a refinery like Pernis, it's one of the biggest refineries in the Shell Group in the Netherlands, or we talk about 20,000 cubes a day. So it's a huge amount, and the water stream is actually equivalent to that of a town of 100,000 people. And there was a fourth very important project premise, namely that it is a zero liquid discharge plant, or a ZLD plant, which means that it was not allowed by the Qatari authorities to discharge any water into the environment. This actually means that all the pots and the pans that you can buy have been installed here. So this slide really shows very nicely these water treatment facilities. Of course, at the background here, you can see the GTL plant, and then here on the forefront of the slide, you can see the water treatment units. So we start here with storage tanks. Storage tanks are always very important because they serve to equalize the water flows and also the components that are present in the water. So you don't want to have any kind of shock loads in a system like this. So after this equalization step, let me go back. The water is being sent to the biotreaters, and in the biotreater we have these bacteria, naturally occurring microorganisms, that oxidize the dissolved hydrocarbons into CO2, and all the ammonia that's present in the water is being converted in two steps via a nitrification-denitrification process into nitrogen gas, which is then emitted into the atmosphere. Since these bacteria are slowly growing organisms, we have to collect them here in these clarifiers, which means that we have a kind of a gravity settlement process. Bacteria, they settle to the bottom part and are being recycled to the biotreater, and the water here, the treated water from the clarifiers, then goes to the membrane units. You can't see the membrane units because they're inside this building, but there's several steps of membranes. So we call them ultrafiltration membranes and reverse osmosis membranes, and the water from those reverse osmosis membranes, it's ultra pure water. So it's really H2O molecules, which is then being used in the GTL process to produce steam. So you have to understand that these membrane processes are actually separation steps. So the somewhat dirty water from the clarifiers goes to the membranes. The clean water is being converted into steam, while the dirty water, so the reject stream from the membranes, goes to the ZLD step, which is not shown in this slide. And in this ZLD step, we apply evaporation and crystallization. So what comes out of the ZLD is actually a kind of a kitchen salt, which is sent to landfill, and the water from the ZLD is again being used as makeup water for the GTL process. So as you can see, it's a very complex plant, highly integrated, and it's also integrated not within, let's say, only the treatment unit itself, but also with the GTL process, which in fact means that if anything would go wrong with this water treatment facilities, also the GTL process here has difficulties. So it's a very critical process step, as critical as the GTL process. So this is one example of where we really manage our water footprint by recycling water. Another example that I would like to show you today is the reed beds in Oman. As you may remember, in his last slide, Frank mentioned the green infrastructures that can be very useful for water treatment, and we have applied those in Oman in the Nimr oil field to treat the produced water. And the reason why these reed beds are so successful is that they are extremely competitive with existing technologies. So the base case for these type of applications is actually that the produced water is being re-injected into the reservoirs, and for that a lot of energy is needed because you have to overcome these high pressure differences. The alternative is to treat the water in the reed beds. You can see the reed here, and you have to realize that the water coming from the formations, deep subsurface, can have a very high salinity. So these reed plants here are tolerant to very high salinities, and that makes them very special. So the water from the reservoir with residual amounts of crude oil droplets is being passed over the reed bed. Then the funny thing is that at the bottom part of the reed bed there are so-called anaerobic but also aerobic bacteria that then convert the organics into CO2. And the way these aerobic bacteria work is that they use the reed here as a kind of a pipe to get the oxygen from the atmosphere to the lower part of the reed bed. And in that way the water is being treated and then being discharged. So you can already see from these two examples that Shell deploys very advanced water treatment technologies, and the only way we can do this is by collaborating with external parties that are specialists in these areas. So in the previous example, the Qatar example, we had a partnership with Veolia and GE and Xenon, who were the vendors of these various equipment units. And here in Oman, we collaborate with a German company called Bauer, who are really the experts in these reed bed technologies. So these are two examples of water management. Technical solutions are being very important. And this brings me actually to one of my last slides in this presentation here. What you can see is that a lot of progress has been made over the last couple of years. We have benefited from the expertise of companies in and outside the energy sector. But there will always be more challenges ahead of us. In the refinery sector, for example, the next challenge will most likely be to reduce trace amounts in the effluent water, like for instance selenium and heavy metals. And we do have special projects to deal with these issues. And in the upstream sector, unconventional gas is still an area where we need to do more work, has already been mentioned by Frank as well. I hope you also appreciate that in driving these technology innovations, we don't think that one company has all the answers. The world moves too fast for that, and some of the best and brightest ideas may be out there. And therefore, I'm also very pleased to participate in this webinar so that we can reach out to you guys who might have solutions for it as well. With this, I would really go to my last slide in this presentation here. It's about the Shell Technology Center in Bangalore. I'm based in Bangalore. We set up this Water Center of Excellence 2 years ago to ensure that all these dispersed water activities in Shell are being connected here. And we do have a fantastic laboratory in Bangalore. The location here now consists of some 900 staff, but we are on a continuous growth agenda, and by 2015 we expect to have some 1,500 colleagues here in Bangalore. And these guys in the water area, they will collaborate happily with people in advanced computational, in catalysis, and so forth. And we also make sure that the knowledge that is being developed in R&D is being handed over to the projects and to the assets. So with this, I would like to thank you for your attention, and I would give the floor back to Karen.
Great. Thank you for that, Albert and Frank, for that presentation. So what we'll do now is open up the floor to all the students on the call to ask any questions to you both. So everyone has to use the chat function in this meeting software to type in any questions that you may have. So I'll just have a quick look to see if there's any at the moment. There is none. So what I'll do is I'll just put everyone on mute just for a couple of minutes in case you need to just have a minute to think about any questions you may have, and then we'll come back here. Okay, thank you. So 2 minutes. Thanks. Okay, Albert and Frank, I've unmuted you both now. I think there are a couple of questions in the chat box if you can look through them. Actually, I'll respond to Kim's question first. Hi, Kim. Thanks for your question. Will the slides in the recording be made available to those not able to attend? Frank and Albert, I think we should be able to share these slides if you can confirm that. And we are recording this session, so once we convert it, we should be able to upload it to our website, shellideas360.com as well. Thanks.
There's no issue with me. Slides can be made
Public?
available.
Oh, great. Thank you very much for confirming that. Okay, so the first question there is from Shao In T, if you would like to answer that one.
That's about the reef bed.
Yeah.
Albert, is that?
Yeah, I can take that one. Is reed bed? Yeah, is reed bed being used to desalinize water in industries today? So the answer is yes, because I showed the example of Oman. There are more examples, but the reed bed is not desalinating the water. It's removing the hydrocarbons from the water. And frankly speaking, since some of the water will evaporate in the reed bed, the salinity levels will increase. Yeah. So it's the alternative to deep well injection, and it's really a huge energy saver. So I think I answered the next one in the same go.
Yeah.
So it can treat saline water, but it's not a desalination technology. So it's resistant towards high salinities. Shall I take the next one as well? I was wondering if using wastewater to generate electricity via turbines is a good way of improving the water efficiency. Well, this is certainly a very attractive method. You have to treat the water anaerobically, so the bacteria convert the organics into methane gas, which can be sent to the turbines to make electricity. However, anaerobic processes cannot operate on pure hydrocarbons. So they can only operate on water that contains compounds like, for instance, methanol, that can be split into methane and CO2. And if that's the case, then indeed it's a very good technology. And we apply this, as a matter of fact, in one of our chemical plants in the Netherlands, Schalmoerdijk. Frank, since you have a background in hydrogen, would you like to take the next one?
Yes, I will try to, Albert, but I do not fully understand it. Oh, so would it be hydrogen generator? Sort of like plug and play hydro generation system in
okay.
pipings.
That's not a clear question. Let's skip that one. That's not a clear question.
No, I don't understand.
Okay, well that's all the questions that we have at the moment.
These are the questions.
Yeah, so if there's nothing else from the audience, maybe we'll just end this a few minutes early. So I'm sorry to everyone for those sound difficulties we had earlier on the call, but we hope you enjoyed the presentation and found everything very interesting and useful and perhaps helpful towards the idea that you may be developing. And thank you again to Albert and Frank for your time this morning.
Yeah, you're welcome.
Great. Okay, thank you everyone. Have a good day.
Pleasure.
All right, goodbye.
Thank you. Bye-bye.
Okay.
Have a good day. Bye-bye.